Tonight, we're going to explore one of the most fascinating categories of objects in the entire cosmos. Objects that exist in a twilight zone of classification, defying the neat boundaries that astronomers have established for centuries. We're going to discover the true nature of brown dwarfs, these mysterious cosmic wanderers that are simultaneously too massive to be considered planets, yet too small to ignite the nuclear fires that define stars. By the end of this journey, you're going to understand a class of objects so peculiar, so abundant, and so revealing about the processes of cosmic creation that they have fundamentally changed our understanding of how matter organizes itself throughout the universe. Before we begin, if you enjoy these deep explorations into the mysteries of space, a quick like or subscribe would really help the channel grow. Now let's begin our journey into the realm of failed stars. In the vast menagerie of celestial objects, we have become accustomed to certain categories. There are stars, those brilliant nuclear furnaces that illuminate the cosmos, converting hydrogen into helium and flooding space with light and warmth. There are planets, those smaller companions that orbit stars, shaped by gravity into spheres, but lacking the mass to generate their own internal fire. And then there are brown dwarfs, objects that refuse to fit neatly into either category, occupying a strange middle ground that challenges our very definitions of what constitutes a star and what constitutes a planet. Imagine, if you will, a ball of gas and dust collapsing under its own gravity in the depths of a molecular cloud. This is how stars are born. As the material draws together, the core grows denser and hotter, pressure building inexorably until something extraordinary happens. At approximately 10 million degrees, hydrogen atoms begin to fuse, creating helium and releasing enormous amounts of energy. A star is born, and it will shine for millions or billions of years, sustained by this nuclear fire in its heart. But what happens when the collapsing gas cloud isn't quite massive enough? What happens when the core never reaches those crucial temperatures needed to ignite hydrogen fusion? The answer is a brown dwarf, an object that forms like a star but fails to cross the threshold into stellar existence. Brown dwarfs are substellar objects with masses ranging from approximately 13 to 80 times the mass of Jupiter. At the upper end of this range, they approach, but never quite reach the mass needed to sustain hydrogen fusion. At the lower end, they hover just above the boundary that separates them from giant planets. This mass range represents roughly 0.012 to 0.075 times the mass of our Sun, a narrow band of cosmic real estate that produces objects unlike anything else in the universe. The name brown dwarf itself is something of a misnomer. These objects are not actually brown. When young and hot, they glow with a reddish hue, similar to the dying embers of a fire. As they age and cool, they transition through various colors, eventually becoming too dim to emit visible light at all, radiating primarily in the infrared portion of the electromagnetic spectrum. The term brown was chosen as a compromise, a color somewhere between red and black, as the astronomer who coined the term once explained. It was meant to suggest something dim, something faint, something that had failed to fully ignite. And in many ways, that description captures the essence of these enigmatic objects. What makes brown dwarfs particularly fascinating is their position as a bridge between the stellar and planetary realms. They share characteristics with both categories. Like stars, they form from the gravitational collapse of molecular cloud material. Like stars, they are composed primarily of hydrogen and helium. Like stars, they can fuse certain elements in their cores, albeit briefly and incompletely. But like planets, they cool over time. Like planets, they have complex atmospheres with weather patterns, clouds, and storms. Like planets, they may even host their own planetary systems, with smaller worlds orbiting around them. The study of brown dwarfs has revolutionized our understanding of stellar formation and planetary science. These objects serve as natural laboratories for investigating the physics of cool atmospheres, the dynamics of cloud formation, and the mechanisms that generate magnetic fields in substellar objects. Every brown dwarf we discover adds to our knowledge of how matter organizes itself across the cosmos, filling in the gaps between the worlds we know and the stars that illuminate them. Tonight, we will journey through the history of brown dwarf discovery, from theoretical prediction to observational confirmation. We will explore the physics that governs these objects, understanding why they fail to ignite hydrogen fusion and what processes sustain them instead. We will examine their atmospheres where iron reigns from silicate clouds and temperatures can range from scorching to frigid. We will meet some of the most remarkable brown dwarfs ever discovered, from our nearest neighbors to the coldest objects ever found, drifting through interstellar space. And we will contemplate the sheer abundance of these objects, potentially numbering in the hundreds of billions throughout our galaxy alone, hidden in the darkness between the stars. The story of brown dwarfs is a story of persistence, of theoretical predictions waiting decades for observational confirmation. It is a story of technological advancement, of infrared detectors becoming sensitive enough to peer into the dimness and reveal what had always been there, waiting to be discovered. And it is a story that continues to unfold today, as new instruments like the James Webb Space Telescope reveal details about these objects that we could scarcely have imagined just a few years ago. So settle in, let your thoughts drift toward the cosmos, and prepare to explore one of the most intriguing categories of objects that the universe has produced. Welcome to the realm of brown dwarfs. Consider for a moment the sheer improbability of what you are about to learn. In an infinite cosmos filled with objects that span an almost unimaginable range of sizes and temperatures, there exists a category of objects that occupies perhaps the strangest niche of all. Brown dwarfs are not merely objects that failed to become stars. They are something altogether different, altogether unique, something that exists precisely because the universe allows for a narrow window of possibilities between the ignition of nuclear fire and the cold darkness of planetary existence. The temperatures inside a brown dwarf can exceed 1,000,000 degrees Celsius, hot enough to melt any material known to science, hot enough to fuse certain atomic nuclei. Yet these temperatures are not quite hot enough, not quite intense enough, to sustain the continuous nuclear reactions that define a star. The brown dwarf sits at the edge of possibility, forever approaching, but never quite crossing the threshold into stellar existence. And yet, from our perspective here on Earth, brown dwarfs present a paradox of abundance and obscurity. They may be among the most common objects in the universe, outnumbering all but the smallest stars. Yet until just a few decades ago, not a single one had been confirmed to exist. They had been predicted, theorized, searched for with increasing desperation. But the darkness hid them well, and the technology to pierce that darkness did not exist. It is only in the last 30 years that brown dwarfs have emerged from theory into reality, transforming from hypothetical curiosities into objects that we can observe, measure, characterize, and begin to understand. Tonight, we will trace this remarkable journey from prediction to discovery. We will understand the physics that makes brown dwarfs possible and the physics that prevents them from becoming stars. We will visit worlds where iron falls as rain and clouds are made of sand. We will meet the brown dwarfs that live in our cosmic neighborhood, some so close that their light has traveled mere years to reach us. And we will contemplate the vast, hidden population of these objects that permeates our galaxy, silent and invisible, drifting through the interstellar void. The universe is full of wonders that we can see with our own eyes. The stars blaze across the heavens, the planets wander among them, the Milky Way arches overhead on clear, dark nights. But there is another universe, equally real but invisible to us, a universe of dim, cool objects that emit no light our eyes can perceive. Brown dwarfs are citizens of this invisible universe, and tonight we will bring them into the light. The theoretical existence of brown dwarfs was predicted long before any were ever observed. In the early 1960s, a young researcher named Shiv S. Kumar was working at the University of Virginia, studying the physics of very low-mass stars. Kumar was interested in a fundamental question that had never been fully answered. How small could a star be? What was the minimum mass required for an object to sustain the nuclear fusion reactions that define stellar existence? In 1963, Kumar published a landmark paper in which he calculated that objects with masses below approximately 0.07 to 0.09 solar masses would never achieve the temperatures necessary to ignite hydrogen fusion in their cores. These objects would form like stars, collapsing from clouds of gas and dust under the influence of gravity. They would heat up during their collapse, glowing with the energy released by gravitational contraction, but they would never cross the threshold into true stellar existence. Instead, their cores would become supported by a different mechanism, one governed by the strange laws of quantum mechanics. Kumar initially called these hypothetical objects black dwarfs, a term meant to suggest their dim, dark nature. However, this name quickly proved problematic. The term black dwarf was already in use to describe a different theoretical object, the final stage of a white dwarf, which would eventually cool over trillions of years until it no longer emitted any detectable radiation. Since no black dwarf in this sense could possibly exist yet, given the age of the universe, there was confusion about what the term actually meant. Alternative names were proposed. Some astronomers suggested calling these objects planetars, a blend of planet and star that captured their intermediate nature. Others proposed substars, emphasizing their position below the stellar mass limit. But none of these terms gained widespread acceptance. The question of what to call these hypothetical objects remained open for more than a decade. In 1975, a graduate student at the University of California, Berkeley, proposed a solution. Jill Tarter, who would later become famous as the director of research at the SETI Institute and the inspiration for the protagonist in Carl Sagan's novel Contact, was working on her doctoral thesis when she needed a term for these objects. She suggested brown dwarf, using brown as a color, somewhere between red and black. The term wasn't meant to be taken literally. Brown dwarfs, as Tarter well knew, wouldn't actually appear brown to the human eye. But the name captured something essential about their nature. They were dim, they were faint, they were cool, and most importantly, they had failed to fully ignite. The term caught on, and brown dwarf became the standard nomenclature for this class of objects. But confirming their existence would prove to be an enormous challenge. Brown dwarfs are inherently faint, emitting most of their radiation in the infrared rather than the visible spectrum. The technology to detect them simply did not exist in the 1970s and early 1980s. Ground-based infrared detectors were imprecise, unable to distinguish the faint glow of a brown dwarf from the overwhelming background noise of the atmosphere. Throughout the 1980s, astronomers launched numerous searches for brown dwarfs, using every technique available. They looked for faint companions around nearby stars. They surveyed young star clusters, hoping to catch brown dwarfs while they were still relatively bright and hot. They monitored stars for the subtle gravitational wobble that would indicate an unseen companion. Time and again, these searches came up empty. False alarms abounded. Objects that initially seemed promising turned out to be very low-mass stars or background objects. The failure to find brown dwarfs became something of an embarrassment for the astronomical community, and some began to wonder whether these objects existed at all. The breakthrough came in the mid-1990s when two independent teams made the first confirmed discoveries, almost simultaneously. In 1994, a Spanish team led by Rafael Rebolo, working at the Instituto de Astrofísica de Canarias, discovered an object in the Pleiades star cluster that they named Teide 1, after the volcanic peak on Tenerife, where their observatory was located. The object was found in images collected on January 6, 1994, using the 80-centimeter telescope at Teide Observatory. Follow-up spectroscopy revealed that Teide 1 had a mass of approximately 55 Jupiter masses, well below the hydrogen-burning limit. Nature magazine highlighted the discovery on its front page, declaring brown dwarfs discovered official. The key to confirming Teide 1's status was a feature known as the lithium test. Lithium is a fragile element that is destroyed at relatively low temperatures, around 2.5 million degrees Celsius. True stars, even the smallest ones, reach temperatures high enough in their cores to burn lithium within the first few 100 million years of their lives. Brown dwarfs, however, never achieve these temperatures. They preserve their primordial lithium, carrying it as a signature of their substellar nature. High-quality spectral data from the Keck telescope showed that Teide 1 still contained its original lithium abundance, proving that its core had never been hot enough to destroy this element. The brown dwarf had been found at last. Almost simultaneously, astronomers at Caltech and Johns Hopkins made another discovery that would prove equally significant. Using the 60-inch telescope at Palomar Observatory, Srinivas Kulkarni, Tadashi Nakajima, and their colleagues discovered a faint companion to the red dwarf star Gliese 229, located just 19 light-years from Earth. This companion, designated Gliese 229b, was unlike anything that had been seen before. spectroscopic observations of Gliese 229b revealed something remarkable. The object's near-infrared spectrum showed strong absorption bands from methane, a molecule that had never been detected in any star. Methane is destroyed at the temperatures found in stellar atmospheres, but it can exist in the cooler environments of planetary atmospheres. Its presence in Gliese 229b's spectrum indicated that this object had a temperature of less than 1,200 Kelvin, far cooler than any star. Jupiter and Saturn, along with Saturn's moon Titan, were the only objects previously known to display methane features. Gliese 229b was clearly something different, something intermediate between a star and a planet. The discovery of Gliese 229b established a new spectral class, the T-dwarfs, characterized by the presence of methane and water vapor in their atmospheres. Along with Tide 1, it represented the first undeniable proof that brown dwarfs existed. After 3 decades of searching, the theoretical predictions of Shiv Kumar had finally been confirmed. Remarkably, nearly 30 years after its initial discovery, Gliese 229b revealed another surprise. In 2024, astronomers using the Very Large Telescope in Chile discovered that what had long appeared to be a single brown dwarf was actually 2 brown dwarfs orbiting each other in an extremely tight binary system. Designated Gliese 229ba and Gliese 229bb, the pair orbits each other every 12 days at a separation only about 16 times the Earth-Moon distance. This discovery resolved a long-standing mystery. Gliese 229b had always appeared too dim for its measured mass. 2 smaller brown dwarfs, each about 34 to 38 Jupiter masses, explained the discrepancy perfectly. The first confirmed brown dwarf had become the first confirmed close brown dwarf binary, demonstrating that even well-studied objects can hold surprises. These discoveries open the floodgates. With improved infrared detectors and dedicated survey programs like the 2-micron All-Sky Survey and the Sloan Digital Sky Survey, astronomers began finding brown dwarfs by the hundreds. The objects that had eluded detection for so long turned out to be remarkably common. Every year brought new discoveries, new records for the coldest or nearest brown dwarf, new insights into the properties of these fascinating objects. The field of brown dwarf research had truly begun. Today, more than 1,800 brown dwarfs have been identified and cataloged. Some are so close to our Sun that they rank among our nearest stellar neighbors. Some are so cold that their temperatures are comparable to a summer day on Earth. And as we will explore in the pages ahead, their diversity and abundance have profound implications for our understanding of how stars and planets form throughout the cosmos. The decades between Kumar's theoretical prediction and the first discoveries were filled with both hope and frustration. Astronomers developed increasingly sophisticated techniques for searching, knowing that brown dwarfs should exist, but consistently failing to find them. The targets of these searches included nearby stars that might have brown dwarf companions, young star clusters where brown dwarfs would be brightest, and open fields of sky where free-floating brown dwarfs might be found. One of the most intensive early search programs was conducted by Benjamin Zuckerman and Eric Becklin at UCLA during the 1980s. They surveyed hundreds of nearby stars using infrared imaging, searching for faint companions that might be brown dwarfs. The search was motivated by theoretical predictions that brown dwarfs should be common byproducts of star formation. Yet despite years of effort, Zuckerman and Becklin found nothing conclusive. Objects that initially seemed promising invariably turned out to be background stars, very low-mass red dwarfs, or instrumental artifacts. The frustration reached its peak in the late 1980s and early 1990s, when several claimed brown dwarf discoveries were later retracted or shown to be misidentifications. A famous case involved HD 11476-2b, discovered in 1989 as a companion to a nearby star. Initial mass estimates placed this object in the brown dwarf range, and it was widely reported as the first confirmed brown dwarf. However, subsequent observations revealed that the object's orbit was seen nearly edge-on, making it appear less massive than it actually was. The true mass remained uncertain, and the object could not be definitively classified. These false alarms and failed searches led some astronomers to wonder whether the theoretical calculations might be wrong. Perhaps the hydrogen-burning minimum mass was lower than predicted, and objects in the brown dwarf mass range did achieve stellar status. Perhaps the formation process somehow prevented objects in this mass range from forming at all. The continued absence of confirmed brown dwarfs was becoming difficult to explain. The breakthrough required not just improved technology, but also a shift in search strategy. Early searches had focused on finding brown dwarf companions to known stars, reasoning that such objects would be easier to locate than isolated brown dwarfs in the general field. But companions close enough to detect were also close enough to be overwhelmed by the glare of their parent stars. What was needed was a way to find brown dwarfs that stood alone without the complicating presence of a brighter stellar companion. The discovery of Tide 1 in the Pleiades star cluster represented exactly this approach. Rather than searching for companions to individual stars, Rebolo and his team surveyed an entire star cluster, looking for faint objects that might be cluster members. The Pleiades, at an age of approximately 120 million years, was an ideal target because brown dwarfs in the cluster would still be relatively warm and luminous, not yet cooled to the point of invisibility. By carefully measuring the colors and motions of faint objects in the cluster field, the team could identify candidate brown dwarfs for spectroscopic follow-up. The confirmation process for Tide 1 involved multiple lines of evidence. First, the object had to be shown to be a true member of the Pleiades cluster, not a foreground or background object that happened to lie in the same direction. This was accomplished by measuring its proper motion across the sky, which matched the motion of other cluster members. Second, the object had to be shown to have substellar properties, which was accomplished through spectroscopy, revealing the presence of lithium and the absence of features associated with stellar mass objects. The discovery of Gliese 229b followed a different path, but arrived at the same destination. Nakajima and his colleagues were conducting an infrared imaging survey of nearby stars, using a coronagraph to block the light of the primary star and reveal any faint companions. When they imaged Gliese 229, a red dwarf star just 19 light years away, they found a faint companion that stood out from the background. Follow-up spectroscopy revealed the telltale signature of methane, a molecule that could not exist in a stellar atmosphere. The nearly simultaneous discoveries of Taida 1 and Gliese 229b in 1994 and 1995 were more than just confirmations of theoretical predictions. They opened entirely new fields of research. Taida 1 became the prototype for studies of young brown dwarfs in star clusters, while Gliese 229b became the prototype for studies of cool, methane-rich brown dwarf atmospheres. Together, they demonstrated that brown dwarfs came in multiple varieties, with different temperatures, different spectral signatures, and presumably different masses. The technological developments that enabled these discoveries continued to advance rapidly in the following years. The 2-micron all-sky survey, known as 2MASS, began observations in 1997 and eventually cataloged hundreds of millions of infrared sources across the entire sky. The Sloan Digital Sky Survey added complementary optical data that, when combined with infrared measurements, could efficiently identify cool, red objects, likely to be brown dwarfs. The Deep Near Infrared Survey of the Southern Sky, or DNIS, provided similar coverage for the Southern Hemisphere. These surveys discovered brown dwarfs by the hundreds, then by the thousands. Each discovery added to the growing census of substellar objects, revealing patterns in their properties and populations. Brown dwarfs were found in star-forming regions, in young clusters, in the general field of the galaxy. They were found orbiting other stars and drifting alone through interstellar space. They ranged in temperature from nearly stellar to barely warmer than room temperature. The objects that had seemed so elusive turned out to be everywhere, hidden only by their faintness. To truly understand brown dwarfs, we must first understand why stars shine. The answer lies in the physics of nuclear fusion, the process by which atomic nuclei combine to form heavier elements, releasing enormous amounts of energy in the process. In the core of our sun, temperatures exceed 15 million degrees Celsius, creating conditions so extreme that hydrogen nuclei can overcome their mutual electrical repulsion and fuse together to form helium. This fusion reaction, known as the proton-proton chain, converts 4 hydrogen atoms into 1 helium atom, releasing energy in the form of gamma rays that eventually work their way to the surface and flood the solar system with light and warmth. The key to sustaining this fusion is mass. A star's mass determines the pressure and temperature at its core. More massive stars have stronger gravity, which compresses their cores to higher densities and temperatures. Less massive stars have weaker gravity and correspondingly cooler cores. There exists a critical threshold, the hydrogen-burning minimum mass, below which an object's core never becomes hot enough to sustain hydrogen fusion. This threshold is approximately 0.075 to 0.08 times the mass of the Sun, equivalent to roughly 75 to 80 times the mass of Jupiter. Objects below this limit are brown dwarfs. But why does this threshold exist? The answer involves one of the strangest phenomena in physics: quantum degeneracy pressure. As a protostar collapses, its core becomes increasingly dense. At a certain point, the electrons in the core become so tightly packed that they begin to resist further compression, not because of their temperature or kinetic energy, but because of the Pauli exclusion principle, a fundamental rule of quantum mechanics that prevents 2 identical fermions from occupying the same quantum state. In a normal gas, Atoms move faster as temperature increases, creating pressure that pushes outward against gravity. But in a degenerate gas, the pressure depends primarily on density rather than temperature. When the electrons in a collapsing object become degenerate, they provide a form of pressure support that doesn't depend on the object getting hotter. This is what saves brown dwarfs from collapsing indefinitely, but it also prevents them from getting hot enough to then ignite hydrogen fusion. The physics unfolds like this. A brown dwarf begins its life as a collapsing cloud of gas and dust, just like a star. As it contracts, gravitational potential energy is converted into heat, and the object grows warmer. In a more massive object, this heating continues until the core reaches the approximately 10 million degrees needed for hydrogen fusion. But in a brown dwarf, the electrons become degenerate before this temperature is reached. The degeneracy pressure halts the contraction, preventing the core from getting any hotter. The object stabilizes at a temperature too low for hydrogen fusion, doomed to slowly cool over the eons. This doesn't mean that brown dwarfs never experience nuclear fusion. Objects with masses above approximately 13 Jupiter masses can fuse deuterium, a heavy isotope of hydrogen that consists of one proton and one neutron. Deuterium fusion occurs at lower temperatures than hydrogen fusion, approximately 1 million degrees Celsius, making it accessible to brown dwarfs. However, deuterium is rare, representing only about 0.0025% of the hydrogen in the universe. A brown dwarf burns through its deuterium supply relatively quickly within the first few 100 million years of its life. After that, it has no internal energy source and must rely on the gradual release of heat accumulated during its formation. The most massive brown dwarfs, those with masses above about 65 Jupiter masses, can also fuse lithium. This fusion reaction occurs at temperatures of approximately 2.5 million degrees Celsius. Like deuterium, lithium is destroyed in this process, which is why the lithium test works as a diagnostic for brown dwarf status. An object that still contains lithium in its atmosphere must either have a mass below 65 Jupiter masses or be young enough that it hasn't yet had time to burn its lithium. One of the most remarkable aspects of brown dwarf physics is the relationship between mass and size. Unlike stars, where more massive objects are larger, brown dwarfs are all approximately the same size as Jupiter. This counterintuitive result arises from the nature of degeneracy pressure. In a degenerate object, adding mass actually causes the object to shrink slightly because the increased gravity compresses the electrons to higher densities. The most massive brown dwarfs are actually denser than their lower mass counterparts, packed into a similar volume by the relentless squeeze of gravity. Because brown dwarfs cannot sustain hydrogen fusion, they must cool over time. A young brown dwarf, freshly formed from a collapsing molecular cloud, might have a temperature of 2,500 Kelvin or higher, glowing with a reddish light, not unlike a very cool star. But without an internal energy source to replenish the heat it radiates away, the brown dwarf grows progressively cooler over billions of years. A billion-year-old brown dwarf might have cooled to 1,500 Kelvin. After 10 billion years, it might be below 500 Kelvin, colder than many planetary surfaces. This cooling process creates a fundamental challenge for astronomers trying to determine the properties of brown dwarfs. A young, low-mass brown dwarf can have the same temperature and luminosity as an old, high-mass brown dwarf. Without knowing the age of the object, it can be difficult to determine its mass. This is known as the mass-age degeneracy, and it complicates attempts to construct a complete census of the brown dwarf population. The cooling also means that brown dwarfs pass through different spectral types as they age. A brown dwarf that starts its life as an L dwarf with clouds of silicate dust in its atmosphere will eventually cool to become a T dwarf, where methane dominates the spectrum. With enough time, it may cool further to become a Y dwarf, the coldest spectral class, where ammonia and water ice begin to appear. The same brown dwarf can be an L dwarf when young and a Y dwarf when old, making the spectral type a poor indicator of mass on its own. The physics of brown dwarfs also has implications for their atmospheres. Because they lack the intense radiation from hydrogen fusion, brown dwarf atmospheres can be cool enough for complex chemistry to occur. Molecules that would be destroyed in stellar atmospheres can form and persist. Clouds of exotic materials, including iron, magnesium silicates, and various sulfides, can condense and create weather patterns unlike anything seen on Earth or even Jupiter. These atmospheric processes make brown dwarfs valuable laboratories for studying the physics of cool, dense atmospheres, with implications for our understanding of giant exoplanets throughout the galaxy. The interior structure of a brown dwarf differs fundamentally from that of a star. In a star like our Sun, the interior can be divided into distinct zones. The core, where nuclear fusion occurs, is surrounded by a radiative zone, where energy is transported outward by photons, and finally a convective zone, where energy is carried by the physical motion of plasma. The boundaries between these zones depend on the star's mass and evolutionary state. In contrast, a brown dwarf is fully convective throughout its interior. From its center to its photosphere, material is constantly rising and falling, carrying heat from the depths to the surface. This convective motion occurs because the interior is too cool and too opaque for radiation to efficiently transport energy. The rising plumes of hot material and the sinking columns of cooled material create a churning, turbulent interior, unlike the relatively stable stratification found in larger stars. The fully convective nature of brown dwarfs has important consequences. In stars with radiative zones, chemical composition can vary with depth because material does not mix across the radiative convective boundary. In brown dwarfs, convection mixes material throughout the entire object, keeping the chemical composition relatively uniform. This means that atmospheric observations can, in principle, provide information about the bulk composition of the entire brown dwarf. The equation of state that governs brown dwarf interiors is also distinct from that of stars. In stellar interiors, matter behaves approximately as an ideal gas with pressure proportional to density and temperature. In brown dwarf interiors, the density becomes so high that quantum effects become important. The electrons are packed closely enough that their wave functions begin to overlap, and the Pauli exclusion principle prevents them from all occupying the lowest energy states. The resulting degeneracy pressure depends primarily on density rather than temperature. This transition from thermal pressure to degeneracy pressure is gradual, occurring over a range of masses and central densities. In the most massive brown dwarfs, just below the hydrogen burning limit, thermal pressure still dominates in the core. In lower mass brown dwarfs, degeneracy pressure is more important. The balance between these two pressure sources determines the internal structure and the potential for nuclear burning. The gravitational binding energy of a brown dwarf is substantial, on the order of 10 to the power of 42 joules for a 50 Jupiter mass object. As a brown dwarf contracts and cools, it slowly releases this stored energy. The luminosity at any given time depends on the rate of energy release, which in turn depends on the structure of the object and the thermal properties of its interior. Detailed evolutionary models track how brown dwarfs cool over billions of years, providing theoretical predictions that can be tested against observations. One interesting consequence of brown dwarf physics is the existence of a minimum temperature. As a brown dwarf cools, it eventually approaches a floor set by the cosmic microwave background radiation, the remnant glow of the Big Bang that pervades all of space. At a temperature of 2.7 Kelvin, a brown dwarf would be in thermal equilibrium with the cosmic background and could cool no further. In practice, no brown dwarf has had time to cool this much, since the universe is only about 13.8 billion years old. But given enough time, the ultimate fate of all brown dwarfs is to approach this minimum temperature, becoming indistinguishable from the cold background of the universe. The question of how brown dwarfs form has occupied astronomers since these objects were first theorized. Do they form like stars from the gravitational collapse of molecular cloud material? Or do they form like planets, growing through the gradual accumulation of solid particles in a circumstellar disk? Or perhaps they form through some entirely different mechanism? The answer, as with many questions in astrophysics, turns out to be complicated. The primary formation pathway for brown dwarfs appears to be similar to that of stars. The gravitational collapse and fragmentation of molecular clouds. Throughout our galaxy, vast clouds of cold, molecular gas and dust drift between the stars. These clouds can span tens or hundreds of light years and contain enough material to form thousands of stars. When portions of these clouds become sufficiently dense, gravity overcomes the internal pressure and collapse begins. As a molecular cloud collapses, it doesn't form a single monolithic object. Instead, the cloud fragments into multiple pieces, each of which collapses independently. This fragmentation process is influenced by turbulence in the cloud, magnetic fields threading through the gas, and the gravitational interactions between forming objects. The resulting fragments span a wide range of masses, from massive protostars that will become hot, luminous stars to tiny clumps that will become brown dwarfs or even smaller objects. The key question is what determines the mass of each fragment. Theoretical calculations suggest that there is a minimum mass for gravitational collapse, known as the Jeans mass, which depends on the temperature and density of the cloud. In typical molecular clouds, the Jeans mass is on the order of 1 solar mass or greater. Yet brown dwarfs clearly form with masses far below this limit. How is this possible? Several mechanisms have been proposed to explain the formation of low-mass objects. One possibility is that turbulence in molecular clouds can create localized regions of very high density, where the effective Jeans mass is much lower than in the cloud as a whole. These dense regions can collapse directly to form brown dwarfs without needing to fragment further. Numerical simulations of turbulent molecular clouds show that this process can produce objects spanning a wide range of masses, including brown dwarfs. Another important mechanism is the fragmentation of circumstellar disks. When a star forms, it is typically surrounded by a rotating disk of gas and dust, from which planets might eventually form. In some cases, these disks can become gravitationally unstable, fragmenting into clumps that can grow into separate objects. If one of these fragments achieves a mass in the brown dwarf range, it may be ejected from the disk before it can accrete enough additional material to become a star. The ejection hypothesis is particularly important for understanding brown dwarf formation. Numerical simulations of star formation consistently show that multiple objects form in close proximity and interact gravitationally. These interactions can be chaotic, with objects exchanging energy and momentum in complex ways. Less massive objects are preferentially ejected from these multiple systems, sent flying into space before they can accumulate enough mass to become stars. In a landmark study published in 2002, Matthew Bate and colleagues at the University of Exeter performed the first hydrodynamical simulation to demonstrate that brown dwarfs are a natural and frequent product of molecular cloud collapse. Their simulation showed that approximately 3/4 of the brown dwarfs formed through the fragmentation of gravitationally unstable circumstellar disks, while the remaining quarter formed in collapsing filaments of molecular gas. In both cases, the key ingredient was dynamical ejection from multiple systems before the objects could accrete to stellar masses. The ejection mechanism has an important observational consequence. It predicts that brown dwarfs should have relatively few close binary companions. When an object is ejected from a multiple system, close companions are typically stripped away. Indeed, observations confirm that binary brown dwarf systems are relatively rare, occurring in only about 5 to 20% of cases, and that those binaries that do exist tend to have small separations of less than about 10 astronomical units. However, the ejection hypothesis cannot be the whole story. In 2009, astronomers discovered the wide binary system 2MEM1101AB, consisting of two brown dwarfs separated by more than 20 astronomical units. This system is too wide to have survived the violent ejection process predicted by simulations. Its existence suggests that at least some brown dwarfs form through a gentler process, perhaps the direct collapse of a small isolated molecular cloud core. More recently, the discovery of the wide binary W215-0AB provided further evidence against universal ejection. This system has a similar mass ratio and binding energy as 2M1101AB, but is older and located in a completely different region of the galaxy. It must have survived any dynamical interactions in its natal star cluster, suggesting that brown dwarf formation does not always involve violent ejection events. The current consensus is that brown dwarfs can form through multiple pathways. Turbulent fragmentation of molecular clouds can produce brown dwarfs directly. Disk fragmentation around young stars can create brown dwarfs that are subsequently ejected. And in some cases, small molecular cloud cores may collapse directly into brown dwarfs without any ejection being necessary. The relative importance of these different mechanisms may vary depending on the environment, with denser, more crowded star-forming regions producing more brown dwarfs through the ejection pathway, and less crowded regions allowing for more direct formation. Another intriguing possibility is that some brown dwarfs form in a manner more similar to giant planets. While most brown dwarfs appear to form from the top down through gravitational collapse, there is some evidence that a few may form from the bottom up through core accretion in a circumstellar disk. This would be the same process that forms gas giant planets like Jupiter and Saturn. However, distinguishing between objects formed by collapse and objects formed by accretion is extremely difficult, and this remains an active area of research. The formation of brown dwarfs continues to be studied through a combination of observations and simulations. High-resolution observations of young star-forming regions reveal proto-brown dwarfs still embedded in their natal material, providing direct views of the formation process. Numerical simulations with ever-increasing resolution can track the collapse and fragmentation of molecular clouds in exquisite detail. Together, these approaches are gradually revealing the full range of mechanisms that produce these fascinating intermediate mass objects. When astronomers first began discovering brown dwarfs in large numbers, they quickly realized that these objects could not be classified using the traditional stellar spectral sequence. The classical sequence, running from hot, blue O-type stars through cooler F, G, K, and M-type stars, was based on the absorption lines visible in stellar spectra. These lines arise from atoms and simple molecules in stellar atmospheres, and they change predictably with temperature. But brown dwarfs are so cool that their atmospheres contain molecules and even dust particles that never appear in stellar spectra. New spectral classes were needed. The first extension to the classical sequence was the L spectral class, defined in the late 1990s to accommodate objects like GD 165b, the faint companion to a white dwarf discovered in 1988. L dwarfs have temperatures ranging from approximately 2,400 Kelvin at the hottest end to approximately 1,300 Kelvin at the coolest. In this temperature range, several important changes occur in the atmosphere. The titanium oxide and vanadium oxide bands that dominate the spectra of M dwarfs disappear in L dwarfs. These molecules are still present in the atmosphere, but at such low temperatures, they condense into solid grains and fall below the visible photosphere. Instead, the spectra of L dwarfs are dominated by absorption from metal hydrides, including iron hydride, chromium hydride, and calcium hydride. Strong lines from neutral alkali metals, particularly sodium, potassium, rubidium, and cesium, also appear. The atmosphere of an L dwarf is a remarkable environment. Temperatures are high enough to vaporize many materials that we think of as solid on Earth, yet low enough for complex chemistry to occur. Clouds of iron droplets and silicate dust form in the upper atmosphere, raining down into deeper layers where they re-evaporate and convect back up. This continuous cycle of condensation and evaporation creates a dynamic, stormy atmosphere unlike anything found around normal stars. As brown dwarfs cool below about 1,300 Kelvin, they transition from the L spectral class to the T spectral class. This transition is one of the most dramatic in all of stellar classification. The silicate and iron clouds that characterize L dwarfs sink below the photosphere, and the atmosphere becomes dominated by methane, a molecule that absorbs strongly in the near-infrared. The prototype T dwarf is Gliese 229b, whose methane-rich spectrum was so unexpected when first observed that it confirmed its status as a truly substellar object. T-dwarfs span a temperature range from about 1,300 Kelvin down to approximately 500 to 600 Kelvin. Throughout this range, methane and water vapor are the dominant absorbers in the near-infrared spectrum. The atmospheres are relatively cloud-free, at least compared to L-dwarfs, giving them a bluish color in infrared images. Some T-dwarfs may have thin clouds of potassium chloride or various sulfides, but these are not as optically thick as the silicate clouds of L-dwarfs. The transition between the L and T spectral classes is not straightforward. Objects at the L/T boundary show complex behavior, with some appearing to be a blend of cloudy L-dwarf and clear T-dwarf characteristics. This has led to speculation that the L/T transition involves the breakup of cloud cover, with holes appearing in previously uniform cloud decks. Some L/T transition objects may be similar to Jupiter, with banded structures and regional variations in cloud coverage. Time-variable observations support this interpretation, showing brightness changes that can be explained by patchy clouds rotating in and out of view. The coldest brown dwarfs belong to the Y spectral class, first identified in 2011 by the Wide Field Infrared Survey Explorer satellite. Y dwarfs have temperatures below about 500 Kelvin, with the coldest known examples having temperatures comparable to or even below room temperature on Earth. At these frigid temperatures, even more exotic chemistry becomes possible. Ammonia, which is destroyed at higher temperatures, can survive in Y dwarf atmospheres. Water, rather than remaining as vapor, may begin to condense into clouds of ice crystals. The discovery of Y dwarfs represented the final frontier in the search for the coolest objects in space. These objects are so faint that they emit almost no visible light at all, radiating entirely in the infrared. Even with sensitive infrared telescopes, they are difficult to detect beyond distances of a few dozen light years. The coldest Y dwarf currently known, WISE 0855, has a temperature of approximately 250 to 285 Kelvin, which translates to roughly -23 to +12 degrees Celsius. This is comparable to a cold winter night on Earth, or even colder, approaching temperatures found in the outer solar system. The L, T, and Y spectral sequence provides a powerful tool for understanding brown dwarf evolution. Because brown dwarfs cool over time, their spectral type changes as they age. A young brown dwarf might start as an L dwarf and gradually cool to become a T dwarf, and eventually a Y dwarf over billions of years. This makes spectral type a function of both mass and age, complicating efforts to determine the properties of individual objects. Within each spectral class, astronomers have developed subclasses ranging from 0 to 9, similar to the scheme used for traditional stellar types. An L0 dwarf is the hottest of the L class, transitioning from M dwarfs, while an L9 dwarf is the coolest, on the verge of becoming a T dwarf. Similarly, T0 is the warmest T dwarf, and T9 the coolest before the transition to the Y class. This fine gradation allows astronomers to track subtle changes in atmospheric properties across the brown dwarf sequence. The spectral characteristics of brown dwarfs make them valuable laboratories for understanding atmospheric physics under conditions impossible to replicate on Earth. The chemistry that occurs in brown dwarf atmospheres, including the formation and dissipation of clouds, the rain of liquid metals, and the photochemistry driven by what little radiation these objects emit, all provide insights into processes that may occur in the atmospheres of giant exoplanets throughout the galaxy. One of the most remarkable aspects of brown dwarf research is the discovery that these objects have weather. Not weather in the meteorological sense we experience on Earth, with rain clouds and thunderstorms, but something far more exotic and extreme. Brown dwarf atmospheres are dynamic environments where clouds form from materials that would be vaporized on Earth, where rain falls as droplets of molten iron, and where storms rage with winds that would make the most powerful hurricanes seem gentle by comparison. The existence of weather on brown dwarfs was first suggested by observations of brightness variability. As astronomers monitored brown dwarfs over time, they noticed that many showed changes in brightness on timescales of hours. These variations couldn't be explained by orbital motions or eclipses. Instead, they pointed to changes in the brown dwarf's own appearance as it rotated. Just as Jupiter shows variations in brightness depending on whether its great red spot is facing toward or away from Earth, brown dwarfs appear to have surface features that come in and out of view as they spin. The interpretation of this variability revolutionized our understanding of brown dwarf atmospheres. Astronomers realized that these objects must have patchy cloud cover, with regions of thick clouds alternating with clearer areas. As a brown dwarf rotates, different portions of its surface come into view, producing the observed brightness changes. By carefully modeling these variations, it became possible to create crude maps of cloud distribution on brown dwarf surfaces. The clouds themselves are nothing like the water ice clouds of Earth or the ammonia clouds of Jupiter. In dwarfs, the clouds are thought to be composed primarily of silicate minerals, including forsterite and instatite, along with iron droplets. These materials condense at temperatures around 1,800 Kelvin, forming a thick haze that shrouds the deeper atmosphere. In some ways, standing in an dwarf atmosphere would be like being inside a sandstorm, except the sand particles are glowing with heat, and the wind is blowing at hundreds of kilometers per hour. As brown dwarfs cool through the L/T transition, these silicate and iron clouds sink below the visible photosphere. The atmosphere becomes clearer, allowing observations to probe deeper layers. But clouds don't disappear entirely. In cooler dwarfs, thin clouds of potassium chloride and various sulfides, including manganese sulfide, sodium sulfide, and zinc sulfide, may form at higher altitudes. These clouds are not as optically thick as the iron and silicate clouds of dwarfs, but they can still produce observable effects. In the coldest dwarfs, a new type of cloud may appear, water ice. At temperatures below about 400 Kelvin, water vapor can condense into ice crystals, forming clouds similar in composition to the high-altitude cirrus clouds of Earth. However, the environment is otherwise nothing like Earth. The water ice clouds would be bathed in an atmosphere of hydrogen and helium, with traces of ammonia, methane, and other molecules. And unlike Earth's clouds, which form at altitudes of only a few kilometers, the clouds on a dwarf would form at enormous pressures, deep within an atmosphere that extends for thousands of kilometers. The weather patterns on brown dwarfs are driven by the same basic processes that drive weather on Earth and other planets. the combination of rotation and convective motions in the atmosphere. Brown dwarfs rotate rapidly, with typical rotation periods of only a few hours. This rapid rotation creates strong Coriolis forces that organize atmospheric motions into bands and zones, similar to the banded structure seen on Jupiter and Saturn. In 2017, a groundbreaking study used data from NASA's Spitzer Space Telescope to create the most detailed picture yet of brown dwarf weather. The researchers monitored 6 brown dwarfs over more than a year, watching each one rotate 32 times. By analyzing the brightness variations during these observations, they discovered that the atmospheric features on brown dwarfs are organized into bands at different latitudes, with each band traveling at a different speed. This banded structure helps explain the puzzling behavior of brown dwarf brightness variations. Earlier observations had suggested that atmospheric features were changing on timescales of less than a day, much too fast to be explained by long-lived storms like Jupiter's Great Red Spot. The new model showed that these rapid changes result from waves propagating through the atmosphere, temporarily thickening or thinning the cloud layers in different latitude bands. The clouds themselves may be relatively stable, but the waves passing through them create the appearance of rapid change. The James Webb Space Telescope has opened a new window onto brown dwarf weather. In 2024, JWST observations of the nearby brown dwarf, binary lumen 16, revealed unprecedented details about their atmospheric structure. The telescope detected silicate clouds with temperatures exceeding 1,000 degrees Celsius, along with signatures of water vapor, carbon monoxide, and methane. Light curves from both brown dwarfs showed significant variability, interpreted as stormy conditions with clouds at various altitudes and gaps between clouds that allowed views into deeper, hotter layers. One of the most intriguing findings from JWST involves the coldest brown dwarf, WISE 0855, at temperatures around 250 to 285 Kelvin. This object is cold enough that water should be condensing in its atmosphere. Models predicted that WISE 0855 should have extensive water ice clouds, similar to the high clouds on Earth. However, early JWST observations found that the spectrum could be well matched by cloudless models. If water is indeed condensing in the atmosphere of WISE 0855, the ice particles may be falling out rapidly, raining down into deeper layers before they can accumulate into visible clouds. This process, called rainout, would be similar to what happens in the Earth's stratosphere, where water vapor is deposited on ice crystals that quickly fall to lower altitudes. The study of brown dwarf weather has implications far beyond these objects themselves. Brown dwarfs serve as analogs for giant exoplanets, objects that are too distant and too faint to study directly. By understanding how clouds form and evolve in brown dwarf atmospheres, astronomers gain insights into processes that may occur on the countless gas giants orbiting stars throughout the galaxy. The techniques developed for mapping brown dwarf surfaces may someday be applied to exoplanets, revealing weather patterns on worlds dozens or hundreds of light years away. Consider what it would be like to descend into the atmosphere of an L dwarf, one of the warmer brown dwarfs with temperatures around 2,000 Kelvin. Based on our current understanding of atmospheric models, your spacecraft would first encounter the upper atmosphere, a region of relatively low density where the pressure is perhaps a few millibars, similar to the stratosphere of Earth. Here, the atmosphere appears to be relatively clear, though traces of dust and haze likely scatter the dim glow that emanates from below. As you descend, the pressure increases, and you begin to enter the cloud decks. The first clouds you encounter would likely be composed of corundum, the mineral that forms rubies and sapphires. These tiny crystalline particles condense from the hot gas, forming a thin haze that models suggest extends for hundreds of kilometers in vertical extent. Deeper still, around temperatures of 1,800 Kelvin and pressures of perhaps a few bars, you enter the realm of the silicate clouds. Here, particles of forsterite and enstatite, along with droplets of liquid iron, appear to form thick layers that can extend for thousands of kilometers. The visibility would drop to nearly zero. The glow from below, the thermal radiation from the deeper, hotter layers of the atmosphere, is filtered and scattered by the dense particulate matter. The iron droplets deserve particular attention on Earth. Iron is a solid metal, useful for construction and industry. In the atmosphere of an L-dwarf, at temperatures exceeding 1,500 Kelvin, iron exists as a vapor mixed with the predominantly hydrogen atmosphere. As this iron-rich gas rises through convective motions, it cools and the iron begins to condense, forming tiny liquid droplets that are still glowing red hot. These droplets fall under the influence of the brown dwarf's gravity, passing through the cloud layers and evaporating again as they reach hotter regions below. The cycle repeats continuously, with iron vapor rising, condensing into rain, falling, and evaporating, driven by the vigorous convection that churns the entire atmosphere. The wind speeds in brown dwarf atmospheres can be extraordinary. Measurements of cloud motion on several brown dwarfs suggest wind speeds of several hundred meters per second, approaching or exceeding a kilometer per second in some cases. These are far faster than any winds on Earth, where the strongest hurricane winds rarely exceed 100 meters per second. They rival the wind speeds measured in the upper atmospheres of Jupiter and Saturn, where jets can reach several hundred meters per second. The energy that drives these winds comes from the brown dwarf's internal heat, conducted upward through the convective atmosphere and converted into kinetic energy through complex circulation patterns. The vertical structure of brown dwarf atmospheres is shaped by the interplay between convection and radiation. In the deepest layers, where temperatures exceed several thousand Kelvin, energy is transported primarily by convection, with hot material rising and cool material sinking in a continuous cycle. As you move to lower pressures and temperatures, radiation becomes increasingly important, with photons carrying energy from the interior towards space. The transition between convective and radiative zones marks an important boundary in the atmosphere, influencing the formation of clouds and the development of weather patterns. One fascinating phenomenon that may occur in brown dwarf atmospheres is the formation of lightning. On Earth, lightning results from the separation of electric charge in convective clouds, with ice particles and water droplets moving past each other and exchanging electrons. Similar processes could occur in the silicate clouds of L-dwarfs or the sulfide clouds of T-dwarfs. The lightning would not look like the brilliant white flashes we see on Earth. Instead, it might glow orange or red, depending on the composition of the atmosphere and the temperature of the plasma channel. Detecting lightning on brown dwarfs is extremely challenging given their distance, but radio observations have revealed bursts of emission that some researchers have attributed to electrical activity in the atmosphere. The day-night cycle on brown dwarfs is essentially non-existent for isolated objects, which have no parent star to illuminate them. The entire surface glows with approximately uniform brightness, heated from within rather than from without. For brown dwarfs that orbit distant stars, any day-night temperature difference would be minimal given the vast orbital distances typically involved. This makes brown dwarf atmospheres fundamentally different from the atmospheres of planets that receive significant stellar irradiation. The weather is driven entirely by internal dynamics, by the flow of heat from the interior towards space, rather than by the differential heating that creates weather patterns on Earth. The chemical composition of brown dwarf atmospheres changes with depth in predictable ways, governed by thermochemical equilibrium. At any given temperature and pressure, certain molecules will be stable, while others will be broken apart or rearranged into different compounds. In the hottest, deepest layers, atoms predominate, with little molecular binding. As you move to cooler regions, molecules become increasingly important. First, simple diatomic molecules like carbon monoxide and molecular nitrogen form. Then more complex molecules appear, including water vapor, methane, and ammonia. The atmospheric chemist can use these patterns to interpret the spectra of brown dwarfs, inferring temperatures and pressures from the observed molecular abundances. Photochemistry adds another layer of complexity. Even though brown dwarfs emit relatively little ultraviolet radiation compared to stars, the small amount they do emit can drive chemical reactions in their upper atmospheres. These reactions can produce molecules that would not be expected from equilibrium chemistry alone, including complex organic compounds. The study of photochemistry in brown dwarf atmospheres is still in its early stages, but it may eventually reveal connections to the prebiotic chemistry that produce the building blocks of life on early Earth. Among the thousands of brown dwarfs now known, several stand out as particularly important for understanding these enigmatic objects. These notable brown dwarfs have taught us about the diversity of properties in the substellar realm, from the warmest and youngest to the coldest and most ancient. The closest known brown dwarf system is Lumen 16, a binary pair located just 6.5 light-years from the Sun in the southern constellation Vela. This system was discovered in March 2013 by Kevin Luman of Pennsylvania State University, who noticed a fast-moving object in images from the Wide Field Infrared Survey Explorer. Follow-up observations revealed that the single moving point was actually two brown dwarfs orbiting each other with a period of about 26 years. Lumen 16 A has a spectral type of L7.5 and a mass of approximately 35 Jupiter masses. Lumen 16b has a spectral type of T0.5 and a mass of approximately 29 Jupiter masses. The cooler member, Lumen 16b, has become particularly famous for its dramatic weather. Observations with the Very Large Telescope in Chile have mapped cloud features rotating across its surface, revealing a turbulent atmosphere with rapidly changing conditions. The brightness of Lumen 16b varies by up to 11% over a single rotation period, indicating large-scale variations in cloud cover. The discovery of Lumen 16 was significant not only because of its proximity, but also because it demonstrated that brown dwarfs could be hiding in our solar neighborhood, waiting to be found by surveys sensitive enough to detect their faint infrared glow. Before Lumen 16 was discovered, astronomers knew of no brown dwarf system closer than about 12 light years. The third closest system to the Sun had been the same since the discovery of Barnard's star in 1916. Lumen 16 suddenly displaced several objects on the list of nearest stars, reminding astronomers that the solar neighborhood still holds secrets to be revealed. The coldest known brown dwarf is WISE 0855, officially designated WISE J 085510.83 minus 0714442.5, discovered by Kevin Lumen in 2014, also using data from the Wide Field Infrared Survey Explorer. Located 7.4 light-years from the Sun in the constellation Hydra, this object has a temperature of approximately 250 to 285 Kelvin, making it the coldest known object outside our solar system. At this temperature, WISE 0855 is actually colder than many locations on Earth and comparable in temperature to Jupiter's upper atmosphere. The mass of WISE 0855 is estimated to be between 3 and 10 Jupiter masses, placing it below the 13 Jupiter mass threshold that conventionally separates brown dwarfs from planets. This ambiguity has led to debate about whether WISE 0855 should be classified as a brown dwarf, a sub-brown dwarf, or a free-floating planetary mass object. The distinction matters less for understanding the object itself than for the philosophical question of how we define the categories of celestial objects. WISE 0855 has become a prime target for studying planet-like atmospheres without the complications of a nearby host star. The James Webb Space Telescope has observed this object multiple times, detecting molecules including methane, water vapor, ammonia, and carbon monoxide in its spectrum. Interestingly, phosphine, which is present in Jupiter's atmosphere, has not been detected in WISE 0855, creating a puzzle for atmospheric chemists. The object may lack water ice clouds despite being cold enough for them to form, possibly because water droplets rain out before they can accumulate. One of the most remarkable brown dwarfs for studying magnetic fields and auroras is SIMP-J 01365663 plus 0933473, typically shortened to SIMP 0136. This object, located about 20 light-years from Earth in the constellation Pisces, was first discovered in 2006. However, it gained particular attention in 2016 when radio observations with the Very Large Array revealed that SIMP 0136 has a magnetic field more than 200 times stronger than Jupiter's, generating powerful auroral emission that can be detected across interstellar distances. When SIMP 0136 was first studied, astronomers thought it was a relatively old, massive brown dwarf. But in 2017, an independent team discovered that it was part of the Carina-Near Moving Group, a collection of young stars traveling together through space. This revised age estimate of about 200 million years meant that SIMP 0136 was much less massive than initially thought, probably only about 12.7 Jupiter masses. This places it right at the boundary between brown dwarfs and planets, making it one of the most planet-like objects ever detected through its magnetic field. The aurora of SIMP 0136 presents a mystery. On Earth and Jupiter, auroras are powered by charged particles from the solar wind, or in Jupiter's case, from its volcanic moon Io. But SIMP 0136 is an isolated object with no parent star to provide a solar wind and no known companion to contribute charged particles. How then does it generate auroras? One possibility is that SIMP 0136 has an as yet undetected companion, perhaps a moon or a small planet, whose interaction with the brown dwarf's magnetic field powers the aurora. Another possibility is that the aurora is generated internally through processes related to the brown dwarf's rapid rotation and strong magnetic field. The prototype brown dwarfs from the 1990s remain important objects of study. Gliese 229b, the first T-dwarf, continues to reveal surprises. As mentioned earlier, the 2024 discovery that this iconic object is actually a tight binary system has required astronomers to revise their understanding. The two components, each with a mass of roughly 34 to 38 Jupiter masses, orbit each other in just 12 days. Their combined methane-rich atmosphere has been characterized in exquisite detail over the decades, revealing the temperature structure and chemical composition of substellar objects. At roughly 900 Kelvin, the Gliese 229b system occupies a middle ground in the brown dwarf parameter space, cool enough for methane but not yet cold enough for ammonia. Tidy 1, the first L-dwarf confirmed through the lithium test, has served as a benchmark for understanding young brown dwarfs in star clusters. Because its membership in the Pleiades star cluster is certain, its age of approximately 120 million years is well determined. This age constraint allows astronomers to test evolutionary models that predict how brown dwarfs cool over time. Epsilon Indi, Ba, and Bb form a binary brown dwarf system orbiting the Sun-like star Epsilon Indi A at a distance of about 1,500 astronomical units. Located just 12 light-years from Earth, these brown dwarfs are close enough for detailed study with ground-based adaptive optics systems. Epsilon Indi Ba is a T1 dwarf with a mass of approximately 68 Jupiter masses, while Epsilon Indi Bb is a T6 dwarf with a mass of approximately 50 Jupiter masses. Together, they span a significant portion of the T-dwarf temperature range, providing a convenient laboratory for comparing the properties of brown dwarfs with different temperatures but identical ages and compositions. Another fascinating system is 2MASSJ 2139266 plus 0220226, commonly shortened to 2M2139, which has become a paradigm for studying brown dwarf weather variability. This L1.5 dwarf, located approximately 47 light-years from Earth, exhibits some of the most dramatic brightness variations ever observed on a brown dwarf, with its infrared luminosity changing by up to 26% over a single rotation period. These enormous swings cannot be explained by simple uniform cloud coverage. Instead, they suggest that 2M2139 has extremely patchy clouds with thick overcast regions adjacent to relatively clear windows that allow views deep into the hotter interior. The brown dwarf 2MASSJ1126 3991-5 003550 A young object belonging to the TW Hydrae Stellar Association at an age of roughly 10 million years provides a window into the early evolution of substellar objects. At such a young age, this brown dwarf is still glowing from the heat of its formation, allowing astronomers to study the atmospheric properties of a brown dwarf that has not yet had time to cool significantly. Young brown dwarfs like this one are particularly valuable because they can be compared to evolutionary models that predict how these objects should change over time. GD 165b, discovered in 1988 as a companion to a white dwarf star, holds a special place in brown dwarf history. Although it was not immediately recognized as a brown dwarf, this object eventually became the prototype for the L spectral class. Its spectrum, with strong metal hydride absorption and weakening titanium oxide bands, provided the template against which all subsequent L dwarfs have been compared. GD 165b orbits its white dwarf companion at a distance of about 120 astronomical units, making it one of the widest brown dwarf companion systems known. The brown dwarf binary WISE-J 1045.5/7-5-3-1906.1, better known as Lumen 16, deserves additional attention for what its detailed study has revealed about brown dwarf interiors. By carefully tracking the orbits of the two components around their common center of mass, astronomers have been able to determine the masses of both objects with unprecedented precision. These mass measurements, combined with age estimates from the kinematics of the system, provide stringent tests of theoretical models that predict how brown dwarfs should evolve. Any discrepancy between the observed and predicted properties would indicate gaps in our understanding of substellar physics. V-J S1-2-5-6b is a particularly intriguing object that blurs the line between brown dwarfs and giant planets. This object orbits a pair of red dwarf stars at a distance of about 150 astronomical units, making it relatively easy to observe without interference from its host stars. The James Webb Space Telescope observed VHS 1256b in 2023 and detected silicate clouds in its atmosphere, along with signatures of water, carbon monoxide, carbon dioxide, and methane. The atmosphere appears to be dynamic and variable, with cloud features changing on timescales of hours to days, at a mass of roughly 12 to 18 Jupiter masses, and an age of only about 140 million years. VHS 1256b straddles the boundary between giant planets and brown dwarfs, making it an ideal laboratory for studying the properties common to both categories. 2. MASSJ 03545-2337+1 13343-7, known as 2M0355, is an unusual brown dwarf that has been used to study the phenomenon of ultracool dwarf variability in exquisite detail. Observations with the Spitzer Space Telescope revealed that this object rotates with a period of approximately 2.8 hours and shows brightness variations that change from rotation to rotation. The most likely explanation is that the cloud pattern on 2M0355 is evolving over time, with new cloud features forming while old ones dissipate. This kind of weather evolution, observed in real time, provides direct insights into the atmospheric dynamics of brown dwarfs. The discovery of each notable brown dwarf has expanded our understanding of what these objects can be. The hottest and most massive approach the properties of very low-mass stars. The coldest and least massive blur into the realm of giant planets. Between these extremes lies a continuous population of objects, each with its own unique characteristics, its own weather, its own magnetic field, its own story of formation and evolution across billions of years. One of the most surprising discoveries in brown dwarf research has been the existence of powerful magnetic fields and brilliant auroras on these substellar objects. Like planets and stars, brown dwarfs can generate magnetic fields through the motion of conducting material in their interiors. But unlike most planets, brown dwarfs can produce magnetic fields of staggering intensity, with implications for how we detect and study these objects across the galaxy. The first hints that brown dwarfs might have magnetic fields came from observations of X-ray and radio emission. In 1999, astronomers using the Chandra X-ray Observatory detected an X-ray flare from LP 944-20, a nearby brown dwarf. X-ray flares are typically associated with magnetic reconnection events, similar to the solar flares that occur on the Sun. The detection suggested that brown dwarfs could have active magnetic fields, despite lacking the radiative cores of stars. Radio observations have proven to be particularly powerful for studying brown dwarf magnetism. When charged particles interact with a magnetic field, they emit radiation through a process called the electron cyclotron maser instability. This radiation is highly directional, creating beams of radio waves that can be detected from Earth if the geometry is favorable. The frequency of the emission is directly related to the magnetic field strength, allowing astronomers to measure field strengths remotely. Using the Very Large Array and other radio telescopes, astronomers have detected radio emission from dozens of brown dwarfs. The observations reveal magnetic fields ranging from a few hundred Gauss to several kilogauss. For comparison, the Earth's magnetic field is about 0.5 Gauss at the surface, while the Sun's field averages about 1 Gauss, but can reach thousands of Gauss in sunspot regions. Some brown dwarfs have magnetic fields more than 200 times stronger than Jupiter's already impressive field. The source of these strong magnetic fields is thought to be a dynamo mechanism similar to what operates in stars and planets. In a stellar dynamo, the rotation of a conducting fluid generates electric currents, which in turn create magnetic fields. The fields are then amplified and organized by the interplay between rotation and convection. In brown dwarfs, the interior is thought to be fully convective, meaning that material is constantly rising and falling throughout the object, combined with rapid rotation. This convection can drive a powerful dynamo. The rapid rotation of brown dwarfs appears to be crucial for generating their magnetic fields. Most brown dwarfs rotate in just a few hours, compared to the 24-hour rotation period of Earth or the 10-hour rotation period of Jupiter. Some brown dwarfs rotate so fast that they complete a full turn in less than 2 hours, approaching the speed at which centrifugal forces would tear them apart. This rapid rotation, combined with vigorous convection, creates ideal conditions for dynamo activity. The magnetic fields of brown dwarfs' power, auroral emission, similar to the northern and southern lights on Earth. On our planet, auroras occur when charged particles from the solar wind are channeled along magnetic field lines into the upper atmosphere, where they excite atoms and molecules that then emit light. Jupiter has similar auroras, but they are powered largely by particles from its volcanic moon Io rather than the solar wind, brown. Dwarf auroras are puzzling because many of these objects are isolated with no star to provide a solar wind and no known companions to contribute charged particles. Yet radio observations clearly detect auroral emission from brown dwarfs floating alone in interstellar space. How this emission is generated remains an active area of research. One possibility is that brown dwarf auroras are powered by internal processes rather than external particle sources. The rapid rotation of a brown dwarf creates strong centrifugal forces that may drive plasma flows in the outer atmosphere. If the plasma breaks away from corrotation with the magnetic field, currents can flow along field lines, accelerating particles that eventually crash into the lower atmosphere and generate auroral emission. This mechanism is similar to what happens on Jupiter, where a portion of the aurora is driven by the breakdown of corrotation in the outer magnetosphere. Another possibility is that brown dwarfs have undetected companions whose interaction with the magnetic field powers the aurora. Even a small moon could contribute enough charged particles to generate detectable emission. Searches for companions around radio-emitting brown dwarfs are ongoing, but so far none have been conclusively detected. The detection of auroral radio emission from brown dwarfs has opened a new avenue for discovering these objects. Traditional searches rely on detecting the infrared thermal emission from brown dwarfs, which limits discoveries to relatively nearby objects. Radio emission can potentially be detected from much greater distances, allowing surveys of more distant regions of the galaxy. This technique may be particularly valuable for finding rogue planets, planetary mass objects that are not bound to any star and are therefore extremely difficult to detect by any other method. Magnetic fields also influence the atmospheres of brown dwarfs in ways that are still being explored. Strong magnetic fields can suppress convection, alter the temperature structure of the atmosphere, and create localized hotspots. Some of the brightness variations observed on brown dwarfs may be related to magnetic activity rather than clouds alone. Understanding the interplay between magnetism and atmospheric dynamics is an important frontier in brown dwarf research. The study of brown dwarf magnetic fields has implications beyond these objects themselves. Brown dwarfs occupy a transitional regime between stars, which generate magnetic fields through partially radiative interiors, and planets, which generate fields through metallic hydrogen or iron cores. By studying how magnetic field properties change across this regime, astronomers can test theories of dynamo generation under a variety of conditions. These insights may eventually help us understand the magnetic fields of exoplanets, most of which are too small and too distant to detect directly. The magnetic environment around a brown dwarf would be a fascinating place to explore if such exploration were ever possible. The magnetosphere, the region of space dominated by the brown dwarf's magnetic field, would extend for many times the radius of the brown dwarf itself. Charged particles trapped in the magnetosphere would spiral along field lines, creating radiation belts similar to Earth's Van Allen belts, but far more intense. Any spacecraft venturing into this environment would need substantial shielding to survive the bombardment of energetic particles. The auroras of brown dwarfs are thought to be concentrated near the magnetic poles, just as they are on Earth and Jupiter. But unlike Earth's auroras, which glow with the greens and reds of excited oxygen and nitrogen, brown dwarf auroras would shine in wavelengths we cannot see. The primary emission is in the radio, detected by our telescopes as periodic pulses when the magnetic poles rotate in and out of our line of sight. Some brown dwarfs also produce optical emission during auroral events, brief flashes of light that can be detected with sensitive photometers. These optical counterparts help astronomers understand the particle energies and atmospheric conditions associated with the auroral process. The connection between magnetism and atmospheric dynamics remains one of the most active areas of brown dwarf research. Computer simulations suggest that strong magnetic fields can influence the formation and evolution of clouds, creating localized features that might be detectable as brightness variations. The interplay between magnetic pressure and gas pressure may create structures in the atmosphere that have no analogy in the non-magnetic atmospheres of planets like Jupiter. Future observations with space telescopes and ground-based adaptive optics systems may reveal these magnetically influenced structures, providing new insights into the complex physics of brown dwarf atmospheres. The boundary between brown dwarfs and other classes of celestial objects has been a source of continuing debate among astronomers. At the upper end of the brown dwarf mass range, these objects approach the properties of very low-mass stars. At the lower end, they blur into the realm of giant planets. Distinguishing between these categories is not always straightforward, and different astronomers have proposed different criteria for drawing the lines. The traditional upper boundary for brown dwarfs is the hydrogen-burning minimum mass, approximately 0.075 to 0.08 solar masses, or about 75 to 80 Jupiter masses. Objects above this mass can sustain hydrogen fusion in their cores and are therefore classified as stars, even if they are extremely cool and dim. Objects below this mass cannot sustain hydrogen fusion and are therefore brown dwarfs. This boundary is reasonably well established from theoretical calculations, but it is not absolute. The exact mass at which hydrogen fusion becomes possible depends on the chemical composition of the object. Objects with fewer heavy elements have higher interior temperatures at a given mass, making fusion easier to achieve. The hydrogen-burning minimum mass for a metal-poor object could be somewhat lower than for a metal-rich object. Nevertheless, the 75 to 80 Jupiter mass range provides a useful dividing line between stars and brown dwarfs. The lower boundary of the brown dwarf class is more contentious. The most commonly cited criterion is based on deuterium fusion. Objects with masses above approximately 13 Jupiter masses can fuse deuterium in their cores during the early stages of their evolution. Objects below this mass cannot fuse any nuclear fuel and must rely entirely on gravitational contraction for their energy. In 2003, the International Astronomical Union Working Group on Extrasolar Planets proposed using the 13 Jupiter mass limit to distinguish between brown dwarfs and planets. Under this definition, an object with a mass above 13 Jupiter masses is a brown dwarf, regardless of where it formed or what it orbits. An object below this mass orbiting a star or stellar remnant is a planet. A free-floating object below 13 Jupiter masses might be called a sub-brown dwarf, a rogue planet, or a planetary mass brown dwarf, depending on who is speaking. This mass-based definition has the advantage of being observationally straightforward, at least in principle. If you can measure the mass of an object, you can classify it. However, the definition has been criticized on several grounds. First, the 13 Jupiter mass limit is not as physically significant as it might seem. The deuterium fusion process is brief and contributes relatively little to the total energy budget of a brown dwarf. Whether an object briefly burned deuterium billions of years ago has little bearing on its current properties. Second, the mass-based definition ignores how objects formed. Planets are generally thought to form through core accretion in a circumstellar disk, building up from small particles into larger and larger bodies. Brown dwarfs and stars form through gravitational collapse of molecular cloud material. These are fundamentally different processes, and some astronomers argue that formation should be the criterion for classification. Under a formation-based definition, a brown dwarf is any object that formed through gravitational collapse but failed to achieve hydrogen fusion. A planet is any object that formed through core accretion in a disk, regardless of its final mass. This definition captures an important physical distinction, but it is difficult to apply in practice. How do you determine whether a distant object formed through collapse or accretion? In most cases, you cannot directly observe the formation process, and the end results can be indistinguishable. The discovery of objects that blur the boundaries has complicated matters further. Some planetary mass objects have been found that appear to have formed through gravitational collapse rather than accretion. These include free-floating objects in young star-forming regions with masses below 13 Jupiter masses, as well as wide companions to brown dwarfs that are unlikely to have formed in a circumstellar disk. Should these objects be classified as planets, brown dwarfs, or something else entirely? One particularly intriguing example is 2M1207b, a companion to the young brown dwarf 2M1207 in the constellation Centaurus. This object was the first exoplanet to be directly imaged, announced in 2004 with follow-up confirmation in 2005. It has a mass of approximately 5 Jupiter masses, well below the deuterium burning limit. However, its wide separation from 2M1207, approximately 40 astronomical units, makes formation through core accretion unlikely. The mass ratio between 2M1207b and its parent brown dwarf also exceeds the threshold typically used to define planets. Under IAU definitions, 2M1207b does not technically qualify as an exoplanet, yet calling it a brown dwarf seems inappropriate given its planetary mass. The term sub-brown dwarf has been proposed for objects that form like brown dwarfs through gravitational collapse, but have masses below the deuterium burning limit. These objects would represent the tail end of the stellar formation process, the smallest fragments that manage to collapse independently. They would be distinct from rogue planets, which are defined as objects that formed in a circumstellar disk but were subsequently ejected from their parent systems. In practice, distinguishing between sub-brown dwarfs and rogue planets is extremely difficult. Both types of objects would have similar masses, temperatures, and atmospheric properties. Without direct knowledge of how they formed, classification is necessarily uncertain. Some astronomers have argued that the distinction is not meaningful and that both types should be grouped together as planetary mass objects, leaving the question of formation to be determined on a a case-by-case basis. The debate over brown dwarf boundaries reflects a deeper question about how we categorize the contents of the universe. Nature does not draw sharp lines between different types of objects. There is a continuum of masses from the smallest asteroids to the largest stars, and the boundaries we draw are conventions that help us organize our thinking. Brown dwarfs occupy a particularly interesting part of this continuum, sharing properties with both stars and planets, challenging us to think carefully about what makes each category distinct. As our exploration of brown dwarfs draws toward its conclusion, we turn to questions of scale and future discovery. How many brown dwarfs exist in our galaxy? How many remain to be discovered? And what will future observations reveal about these fascinating objects? The first attempts to estimate the brown dwarf population were based on observations of the solar neighborhood. Within about 30 light-years of the Sun, astronomers have conducted relatively complete surveys for brown dwarfs, using infrared observations to detect objects that would be invisible in optical light. These surveys revealed that brown dwarfs are common, with roughly one brown dwarf for every 5 or 6 stars in the local volume. Extrapolating this ratio to the entire Milky Way galaxy is challenging because the stellar population varies with location. The solar neighborhood may not be representative of the galaxy as a whole. Nevertheless, initial estimates suggested that the Milky Way might contain tens of billions of brown dwarfs, a substantial population that had been hidden in plain sight, too dim to detect until the advent of sensitive infrared surveys. More recent studies have revised these estimates upward. In 2017, an international team led by Koralska Music used the Very Large Telescope to survey the young massive star cluster RCW38, located about 5,500 light-years from Earth. In this cluster, they found approximately one brown dwarf for every 2 stars, a much higher ratio than had been measured in the solar neighborhood. Combined with observations of other star-forming regions, this result suggested that brown dwarfs form in abundance throughout the galaxy. Based on these observations, the current estimate for the brown dwarf population of the Milky Way is between 25 billion and 100 billion objects. This is comparable to the estimated number of stars in the galaxy, which ranges from 100 billion to 400 billion, depending on assumptions about the mass function. If the higher estimates are correct, there may be nearly as many brown dwarfs as stars in the Milky Way, a vast population of dim, cool objects drifting through interstellar space. Even this estimate may be conservative. The surveys used to measure brown dwarf populations can only detect objects above a certain minimum mass, typically about 3% of the solar mass, or roughly 30 Jupiter masses. There may be many more lower mass brown dwarfs and sub-brown dwarfs that fall below the detection limits of current instruments. The true population of substellar objects could be even higher than current estimates suggest. The abundance of brown dwarfs has implications for our understanding of star formation. The initial mass function, which describes how many objects form at each mass, extends smoothly from massive stars down through brown dwarfs. This suggests that brown dwarf formation is not a special process, but rather a natural extension of star formation to lower masses. The same mechanisms that produce stars also produce brown dwarfs, just at the lower end of the mass spectrum. Future surveys will dramatically expand our knowledge of the brown dwarf population. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, a 10-year imaging program that will detect objects far fainter than current surveys can reach. Because brown dwarfs emit most of their light in the infrared, and the Rubin Observatory's camera extends into near-infrared wavelengths, it will be particularly effective at finding cool brown dwarfs at greater distances than previously possible. The Rubin Observatory is expected to detect ancient brown dwarfs in the Milky Way's halo, objects that formed early in the galaxy's history and have been drifting through space for billions of years. These ancient brown dwarfs carry information about conditions in the early universe, preserved in their atmospheres and their motions through space. By studying them, astronomers can learn about the formation history of the Milky Way and the processes that created our galactic home. The James Webb Space Telescope has already revolutionized brown dwarf science, providing detailed observations of atmospheric composition and structure that were impossible with earlier instruments. JWST is particularly well suited to studying the coldest brown dwarfs, whose emission peaks in the mid-infrared wavelengths where the telescope is most sensitive. Continued JWST observations will characterize the atmospheres of dozens or hundreds of brown dwarfs, building a comprehensive picture of how these objects evolve over cosmic time. The European Space Agency's Euclid mission, launched in 2023, will also contribute to brown dwarf science, despite its primary focus on dark energy and dark matter. Euclid's deep near-infrared surveys will detect faint brown dwarfs across large areas of sky, potentially discovering objects at greater distances than previous surveys could reach. The mission's precise measurements of stellar positions and motions will help identify brown dwarfs through their high, proper motions, the apparent movement across the sky that results from their proximity to Earth. Looking further ahead, the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field infrared surveys that promise to transform our understanding of the brown dwarf population. Roman's infrared camera will be capable of detecting brown dwarfs throughout much of the Milky Way, not just in the immediate solar neighborhood. The mission is expected to discover thousands of new brown dwarfs, including many in the coldest Y dwarf class that are currently almost impossible to find. Ground-based radio telescopes offer another avenue for brown dwarf discovery. The detection of auroral radio emission from brown dwarfs has demonstrated that these objects can be found through their radio signatures, even when they are too faint to detect in infrared surveys. The square-kilometer array, when completed, will be orders of magnitude more sensitive than current radio telescopes, potentially detecting brown dwarfs at distances of hundreds or thousands of light years. This technique may be particularly valuable for finding the elusive, free-floating, planetary mass objects that are too cold and too small to detect through thermal emission. Gravitational microlensing provides yet another method for detecting brown dwarfs. When a brown dwarf passes between Earth and a distant background star, its gravity bends and magnifies the light from the more distant star. By monitoring millions of stars for these brief brightening events, astronomers can detect brown dwarfs regardless of how faint they are intrinsically. Several brown dwarfs have already been discovered through microlensing, and future surveys like those planned for the Roman Space Telescope will dramatically increase the sensitivity of this technique. The combination of all these observational approaches will provide a comprehensive census of the brown dwarf population in the coming decades. We will learn how the brown dwarf mass function extends to ever lower masses, approaching and perhaps crossing the boundary with free-floating planets. We will understand how the ratio of brown dwarfs to stars varies with environment, from dense star-forming regions to the sparse field population, and we will characterize the oldest brown dwarfs in the galaxy, objects that have been cooling for billions of years and now approach the temperature of the cosmic background. The study of brown dwarfs has broader implications for understanding planets throughout the galaxy. Brown dwarfs and giant planets have similar atmospheric temperatures and compositions, making brown dwarfs valuable proxies for studying planetary atmospheres. Techniques developed for analyzing brown dwarf spectra can be directly applied to giant exoplanets, helping astronomers characterize worlds too distant to observe directly. Brown dwarfs also raise intriguing questions about habitability. While no one expects life to exist on a brown dwarf itself, these objects could potentially host planets or moons in their own miniature solar systems. A planet orbiting close enough to a young brown dwarf could receive enough heat to maintain liquid water on its surface. As the brown dwarf cools over billions of years, this habitable zone would migrate inward, but for limited periods, conditions might be suitable for life. Theoretical studies have shown that habitable zone durations of 1 billion years or more are possible for planets orbiting brown dwarfs with masses above about 0.04 solar masses. This is long enough for life to potentially emerge and evolve, although the changing conditions would present challenges for any organisms. The proximity required for habitability would also mean that such planets would be tidally locked, with one face permanently turned toward the brown dwarf, creating extreme temperature contrasts between the day and night sides. As we contemplate the vast population of brown dwarfs in our galaxy, we are reminded that the universe is far richer and more complex than it first appears. For most of human history, we saw only the stars, the bright beacons that light the night sky. Now we know that for every star we see, there may be an equal number of brown dwarfs, dim and cool, invisible to our eyes, but no less real. These failed stars populate the darkness between the stars, silent witnesses to cosmic history, each one a unique outcome of the processes that shape matter throughout the universe. We have journeyed through the realm of brown dwarfs, from their theoretical prediction in the 1960s to the cutting-edge observations being made today. We have explored the physics that governs these objects, understanding why they fail to ignite hydrogen fusion and how they slowly cool over billions of years. We have examined their exotic atmospheres, where iron rains from silicate clouds and temperatures range from scorching to frigid. We have met some of the most remarkable brown dwarfs ever discovered, from our nearest neighbors to the coldest objects in the known universe. And we have contemplated the sheer abundance of these objects, potentially numbering in the tens of billions throughout our galaxy alone. The story of brown dwarfs is a reminder that the universe does not conform to our neat categories. These objects exist in a twilight zone between stars and planets, challenging us to think carefully about what defines each class. They form through the same processes as stars, but fail to achieve stellar ignition. They have atmospheres like giant planets, but formed through gravitational collapse rather than accretion. They are neither one thing nor the other, but something unique, something that expands our understanding of what the cosmos can create. The study of brown dwarfs has implications that extend far beyond these objects themselves. By understanding how they form, we learn about the processes that create all types of objects, from molecular clouds. By studying their atmospheres, we develop techniques that can be applied to exoplanets throughout the galaxy. By measuring their magnetic fields, we gain insights into dynamo mechanisms that operate across the stellar planetary divide. Every brown dwarf we discover and characterize adds to our knowledge of how matter organizes itself under the influence of gravity, chemistry, and physics. Perhaps most profoundly, brown dwarfs remind us of what remains to be discovered in our own cosmic neighborhood. The closest brown dwarf system, Lumen 16, was found only in 2013, less than 2 decades ago. The coldest brown dwarf, WISE 0855, was announced in 2014. The solar neighborhood that we thought we knew well has turned out to harbor entire classes of objects that were completely unknown until recent years. What else might be hiding in the darkness between the stars, waiting for telescopes sensitive enough to reveal them? When you look up at the night sky, you see only the stars, the brilliant points of light that have guided humanity since the dawn of civilization. But now you know that between those stars, invisible to your eyes but no less present, drift countless brown dwarfs. Some are young and warm, glowing with a reddish light that no human eye will ever perceive. Others are ancient and cold, barely warmer than the cosmic microwave background radiation that pervades all of space. Each one is a world unto itself, with its own atmosphere, its own weather, its own magnetic field, its own story of formation and evolution across billions of years. The universe is far stranger and far more wonderful than our ancestors ever imagined. Brown dwarfs are just one example of the unexpected riches that await discovery when we develop the tools to look beyond the obvious. They remind us that nature is endlessly creative, producing outcomes that we never predicted, filling niches that we never knew existed. And they inspire us to keep looking, to keep questioning, to keep exploring the cosmic darkness in search of whatever other wonders might be waiting there. Thank you for joining me on this journey through the realm of failed stars. If you found this exploration meaningful, please consider liking and subscribing to the channel. Your support helps me continue making these deep dives into the mysteries of space and our place within it. Until next time, keep looking up at the night sky. Keep wondering about what lies in the darkness between the stars. Keep marveling at the fact that we, small as we are, and brief as our lives may be, can understand something as vast and distant and strange as a brown dwarf. The universe is full of objects that defy our expectations and challenge our categories. Brown dwarfs are one of the most fascinating examples, cosmic misfits that are too big for planets and too small for stars. But in their very existence, they teach us something profound about the universe. That nature does not respect the boundaries we draw, that the cosmos is far richer and more complex than any classification system can capture, and that the darkness between the stars holds secrets we are only beginning to unveil. Sleep well tonight, knowing you share this cosmos with billions of brown dwarfs, each one a testament to the universe's endless creativity. And remember, The next great discovery might be lurking just at the edge of detection, waiting for someone with the curiosity and persistence to find it. Good night.